Right. So the first talk is Ceren Vardar Acar, and the topic is exit times and extremes of fractional Brownian motion in Levy processes.
Thank
Please,
you very
Ceren,
much.
thank you.
So I would like to start with thanking organizers for the opportunity and the lovely workshop series for the protection course and the other with so I want to talk about the two times and things of fractional Brownian motion and Levy process, as some of the extremes are ideally related to the heavy tail phenomena. Or how to deal with it. First, I would like to start by talking about the main extreme value that I want to present. So it's going to be maximum drawdown, which is highest possible drop for any process with the oscillations in it, and the exact distribution for the maximum loss for Brownian motion with no drift case was given in 1999, and later on some below in 2007 also present the same result, and asymptotic expressions for Brownian motion were found around vote for the expected value and the distribution around 2004, and the motivation actually comes from measuring the performance of a stock and also measuring risk of a stock, where it can be used in the actuarial science and portfolio optimization type problems. And so a while ago, we were working on crude oil data, whether to decide whether the business cycle maybe ended or it's still going on. What we mean by business cycle was actually this kind of excursion going upwards and downwards for a long time. So maximum draw up and maximum drawdown. If that cycle has ended, then the investors could decide on investing on such a stock or not. But what we saw was the heavy tail, and once the moving upwards trend starts, the stock continues to move upwards with some corrections for a long time, and same thing occurs with the drawdown. So actually there is a dependence between the increments. So we would like to model such a data through fractional Brownian motion, but that's a Gaussian process, and the log returns exhibit heavy tails, especially actually while playing with filtering and trying to smooth out some of the extremes. We saw that this heavy tail was arising because of these unforeseen jumps downwards. So we didn't have to play with the value of maximum draw up, but we had to play with the value of maximum drawdown. And so those jumps actually correspond to 2008 crisis, the first one, and those downward jumps. And the very last one corresponds to the pandemic. They are both unforeseen events. And but once we...
Sharon, maybe we can do without a mic, because there is this crackling noise. Let me just take it. I mean, there's a mic in the room and it's picking up.
Oh, thank you. So once we did the filtering on those jumps that occur during those extra events, we were actually able to come back to Gaussian distribution from that heavy tail distribution. And the dependence was still there, and the business cycle, we didn't lose much of an information on the business cycle, just a bit due to extreme events. And so we were able to fit the fractional Brownian motion for the asset price, which the solution of Black-Scholes model for the asset price goes like this, where mu is the drift term and sigma is the diffusion coefficient. And by taking the logarithm of the stock prices, actually, we have the fractional itself. And so what is the fractional Brownian motion? So for a standard fractional Brownian motion, we can say that it has this Hurst parameter, which explains the dependence between the increments in the process, and it's a Gaussian continuous centered Gaussian process with the through the dependence between the increments, we have this covariance function on the values of the fractional Brownian motion. And it has stationary increments. Whenever you have the same time difference for the increments, you have the same law, and it is positively correlated for Hurst parameter greater than 1/2. So once the increments start to go up, it tends to go up for a long time, and once the increments start to go down, it tends to go down again for a long time for Hurst parameter greater than 1/2. And they are negatively correlated for age less than 1/2, and the fractional Brownian motion actually can exhibit long range dependence in the data set whenever we have this first parameter also greater than 1/2. And it has this self-similarity property, so it can be explained like we have as we zoom in and zoom out of the process, or as we do scaling in time, it would be identical in law with scaling in space. In this way, again, as a function of Hurst parameter. And so I would like to, because the talk is on the extremes, and to bring heavy tail distribution to a regular Gaussian distribution, because we had to play with the extreme values, I would like to introduce the notation as well. And the infimum of the process, so we have fractional Brownian motion with drift and diffusion. I is the infimum, S is the supremum, and R is the range. And this first exit time or first hitting time of fractional Brownian motion of a certain level is denoted by age A, and the maximum loss, the formal definition for the maximum loss is if you move forward in time and look at the differences, which can be done also by fixing the value of future time, the value of future time, and looking at the differences and looking at the supremum of the differences, which is the loss process, which is called as the loss process, and highest loss will give the maximum loss of the whole process. And because maximum loss results are also related to this reflected fractional Brownian motion, I would also like to introduce this. So the absolute value of fractional Brownian motion without the rest case here, and tau represents tau1 represents the first hitting time of level 1 for the reflected fractional Brownian motion, and I will use RS for the supremum of the reflected fractional Brownian motion. So the first result is on the law of supremum of the reflected. The square of the supremum is actually identical in law with some function of hitting time, that fractionals hitting time, and square of the supremum of the regular fractional Brownian motion is again identical in law with its function of hitting time. And so these equivalents actually lead to bounding first moment and second moment of the supremums, and that also gives us a bound on the tail probability of the supremums. And the proof is just by scaling property of fractional Brownian motion. So if we consider the law of heating time on the reflected fractional, then for the tail probability of this heating time, for heating level 1 for this process occurs later than some time, is equivalent to the event that the supremum up until the time is less than level 1. And so we can rearrange this time and use the scaling property here, and we have the relation between the heating time and the supremum of the process. So then by splitting the square, we have the equivalence. And also for the reflected fractional Brownian motion supremum, whenever it's less than certain value, it means the infimum is greater than that negative of that value. And this event's measure is bounded above by supremum only being less than certain value, and that gives a relation between regular supremum of the regular fractional Brownian motion and supremum of the reflected fractional Brownian motion. So by following the same arguments over here, the descaling, play with time and space, we can see that supremum square is identically low with its heating time of level 1. And once we have these relations, we can excuse me, bound this law of supremum of reflected and supremum of the regular process by the heating time, and using the gamma distribution property by taking theta over here as the expectation of this function of heating time, and by just taking k as 1 in the gamma property, we can have an upper bound for the second moment of both processes, supremums, and which is written in terms of this theta, and which is actually as we plug it in the gamma density, which gives us Laplace transform of the heating time, and this Laplace transform for the fractional Brownian motion, it was shown that by Molar is bounded above such an exponential function, And so using that and by taking the integral, we have actually simple upper bound for the second moment, and which leads us to obtain by just applying Jensen and Markov inequality afterwards, which leads us to obtain upper bound for the tail law of the supremum of the process, and which actually also leads us to obtain upper bound for the tail of the reflected. And also in 1997, for the supremum, the first moment of the supremum for fractional Brownian motion by Noros, there were upper and lower bounds. And using that result, we were actually able to obtain bounds on the maximum drawdown for fractional Brownian motion with drift and diffusion case. And this maximum loss is by only using the relation actually with maximum loss and the range and the infimum of the process. And those also give us bounds on the law 2. And so by using Noros result, supremum is bounded above by, for a drift case, bounded above by such an expression, and carefully considering the value of the drift, whether it's negative or positive, we can find upper bound for the first moment of the range, and maximum loss is going to be always less than the range for any process, and it's going to be always greater than the minus infimum of any process. So by definition, it has such bounds anyway. So this actually gives us again tail law bound for the maximum loss, and for the lower bound, what we have is we just use the definition of maximum loss, and if one of them is already greater than x, that would imply the whole maximum loss being greater than x. So, and one of the difference means here actually the difference, it corresponds to the difference of the values of fractional Brownian motion from 0 to t. And this is the law of such a difference. So it's bounded below by Gaussian distribution in such a way. And for the inequality again, for the lower bound, the maximum loss is bounded below by minus infimum to any process by definition. So we can also use that for the first moment bounds. And to identify the first moment of minus infimum, we use the bounds on the supreme, of course. And so this gives us actually very nice bounds on the first moment of maximum loss up until time 1 for a process. And using the rescaling property, it can be generalized to any time, any fixed time t. And they are very nice, simple values. And for actually later on, we were able to obtain tighter bounds on the maximum loss of the process. These are much closer bounds. And this was done by Stokoe-Fernick inequality and just by binomial expansion. But I'm going to skip the details for this one. And so we also have tighter bounds and by just using the rescaling, we can generalize this to any time t. And how would these be useful? I think if we know such bounds, then that means to come back to from a heavy tail distribution to come back to regular Gaussian distribution and make calculations maybe faster. We can try to keep the maximum drawdown in certain values. As for the loss process, when the drift is zero, there's no drift. Again, we have self-similarity property, and also because the fractional Brownian motion has stationary increments, such an increment will have the same law as this one for fixed value of v, and and both will be zero mean Gaussian processes with such a covariance function. So their supremums will be having the same law as well. So the loss process has the same law as the supremum of the fractional Brownian motion. That actually gives the earlier bounds for those extra jumps that occur during extreme events. Those loss actually are also are having same law as the supremum of the fractional Brownian motion. And there is also Talagrand's result on the supremum of a Gaussian process when the time space is a compact space, and when the process has almost surely bounded sample paths, we have this supremum law as the value gets high, same as the Gaussian distribution. To be able to have this, I mean, this is an equivalent event to these two conditions. So if there exists a unique time t in this compact set where you have the highest variance value, and that variance you take it as alpha square, and also you define a new time space where in this time space the covariance between that highest variance value and the other values are greater than alpha square minus h square for some h greater than 0. And when you have such a time space, on that time space, if you have this limit at 0, or this loss process first moment in order h, if you have such a limit, then if you have those two conditions, then you have this result. Or if supremum, it's equivalent case. So we wanted to, because the maximum loss is the maximum of the loss process, and the loss process is also a Gaussian process, we wanted to apply Talagrand's result on the maximum loss. And for Hertz parameter greater than 1/2, and for fractional Brownian motion with drift and diffusion case, we actually have the same result. And for the first condition, the maximum loss is the supremum of these differences, and capital T is here the compact set, and space of time, and T FBM has continuous sum. It's a Gaussian process, and we just need to, show those two conditions of telegraph result. And the alpha square here is corresponding to the highest variance of those differences which occur actually, and it's a really unique variance, and it occurs on the unique time, and for the difference of y0 minus yt, so the alpha squared, that's the highest variance difference can have. So the alpha squared here is sigma squared 2 to 2h. And that difference from 0 to t has drift minus mu t and the diffusion parameter sigma. So therefore, we expect the limiting distribution to be in this form for the maximum loss. As for the condition 2 of the Lagrange lemma, this stands in for tau, the unique time that gives the highest variance, and the th, this new th is the covariance between the differences and that highest variance value. And so this th, as we write it, explicitly, what we have is this covariance function, and being greater than sigma squared t to 2h minus h squared. And so the condition 2 becomes this one, as in equation 14 in the Lagrange lemma. And that second condition can be actually bounded above by just taking supremums separately on the drift terms and on the loss terms. And so in order to identify TH, we look at the fractional Brownian motion covariance function, just this one. And for every u and v time u and v in TH, we have this bounding by the property of TH. So that means for a fixed u bar, this inequality is also satisfied. So the time space for a fixed u bar, the TH we have is in this form. Now, if we fix the u bar for a value being greater than t over 2, then we have this term negative, this term positive. So that gives us v to t 2h being greater than such a bound. And on the other hand, if we fix the u bar for a value being less than t over 2, then we still have the same lower bound as the previous one. So for any u bar, this is the characterization of this th u bar for a value of v. So for any u bar in such a space, v will follow such a time v will follow such a bound. And this is just a convex function, so just by using the property of it being above all of its tangent lines, we get to observe this inequality then, because we have t to 2h minus v to 2h bound in this form. And this inequality gives us nicer lower bound on the time values of V in that space. So having V for a fixed U bar, having V in TH means actually having conditions of this and this on the time V. And also for a fixed U bar, we have the expected value. This is a centered, fractional Brownian motion V. So we have the 0 as the expected value. So this limit is actually can be written in this form by also using the stationarity of the increments, which actually gives us for a fixed U bar. And by using earlier lemma on the lemmas or results on the first moment of supremums, the upper bounds, we can bound this limit above by these expressions. And so just by dividing it by age, and we have the result. So we get the limit to be 0 in the order of age. And because this compact set is, and we have separable Gaussian, a monotone convergence argument will extend these results to from fixed U bar to any U in the space. And as for the drift part of the bound, again, here is the inequality we have for TH, and by using the reverse triangular inequality on the left hand side, we can see that V minus U to H is bounded below by this, and just like V being greater than that same lower bound, by using V minus U bar in place of V, we have the same lower bound. So actually the drift term is also converging to 0 as in order of H. And so this tells us the maximum loss tail probability decays exponentially. So we can get the no drift case, of course, from here. So we have, I mean, for high values of maximum drawdown, we know how to manage it now. And also I had the rest of the talk on the spectral negative Levy process, but I'm just going to mention them. And so spectral negative Levy is just having negative drops, and we have the same functionals of the process: maximum drawdown, maximum draw up. And here we are using completely different proof to have the distribution. This time we have the exact distribution, but here we are using excursions from one point to, or one level to the same level, and actually excursions under the supremums, and using the property that those excursions follow Poisson point process, and the depth of the excursions correspond to the loss in time, and the highest depth of the excursion corresponds to the maximum loss. And and using the scale function of spectral negative Levy, we were able to obtain the joint density of the infimum and maximum loss of the process. And from here, we can get exact distribution of the maximum loss up until hitting certain level of beta in terms of scale functions of Levy process. So once we have the parameters related to the Levy process, then we actually have the exact distribution of the maximum loss. And also from here, maximum loss and maximum gain joint distribution is observed. This is in 2017. And from here on, there were results on the 3 exit time of spectral negative Levy process, considering loss exit time, loss process exit time, and the processes itself passage times, and from a rectangular region. And later on, that rectangular region, we changed it into trapezoid region, exiting from a trapezoid region by using affine functions in the orders. And that result was in 2020. And so this is all I would like to talk about. Yeah.
Thank you.
Thank you.
Questions? Comments?
I have a naive question. Yes. How many moments, power moments may the maximal have? Maximum fractional Brownian motion. It may have finite power moments. Yeah. How many moments might have?
I don't know. I don't
Maybe
know.
100, yeah, 1,000 moments, yeah. Okay.
I guess so.
Yeah, because
because
if you look at the page 10, when you use Markov inequality, go to page 10, for example, formulation, yeah.
Gamma trick.
Yeah. So okay, yes, you use Markov inequality, you formulate that result, and upper bound is at the bottom. You see, it doesn't have even first moment with respect to x. No moment, no power moments at all. Upper bound. How precise is the upper bound? I'm just wondering if you use this.
Actually, the Laplace transform of the heating time for fractional Brownian motion, which is related to the density of the supremum, using Malieva calculus, they were able to show that only it has a bound because of the dependent increments. It's not possible to obtain exact values. So even for the moments, there are asymptotic expressions, and yes, I mean, it would be possible to write them, but I mean, as far as I know, that's the highest technique they are able to use for fractional Brownian motion, the Malieva calculus, and those even only give bounds on the distributions. So that's the thing about fractional Brownian motion.
Go back a few slides. Then you used like a gamma trick, Fubini. Then you could try that to get maybe more moments in a short.
Yeah.
And essentially, you have some control on the Laplace transform, and you can try to turn that into.
It would be possible to write all in terms of
So you started with a finance model, like Black-Scholes model, yes, driven by this fractional FBM. Yeah. So I mean, of course, you didn't do any pricing or hedging or anything like that. But this, this is not the same martingale, so it's as arbitrage this model, right? But this doesn't influence what you're doing at all, right? Because
For the
You're looking
arbitrage,
under the real world measure.
yes, yes. But for the arbitrage, actually, they say fractional Brownian motion actually leads to arbitrage
Yes,
case.
yes, not
And
same
but-
martingale, yeah,
but
sure.
If you, yeah, but they,
Change
if we
measure.
have very high frequency data,
Yes,
then that fractional, I think they showed already that the arbitrage case is not there anymore. So.
I mean, the problem is that you cannot change, there's no equivalent local martingale measure
Yeah.
for the model,
Yeah,
so you
yeah.
cannot relate, and
Yes.
that will,
Uh-huh.
by the fundamental theorem of asset pricing, lead to
Yes,
arbitrage, right?
yes.
So now how to exploit that, that's a different story, but I guess here it doesn't matter because you're really looking
So
at the real
theoretically,
world measure, you're
yeah.
looking at some.
Uh-huh.
Thank you.
Thank you.
Okay, if there are no other questions, we thank the speaker again.